This video will address for us how to calculate average atomic mass. If we take a look at the element block that conveys the atomic number and then a number with digits after the decimal place, this number is most properly known as the average atomic mass. It is a weighted average. We take into account the percent abundances of each isotope of the element, as well as the individual mass assignments of the isotope. So it's not a straightforward average, it's a weighted average. And so to show us how we get that, now first, in Unit 3 only, Chapter 3, will we deal with the unit of an AMU. This stands for Atomic Mass Unit. We know commonly that when we're dealing with mass, the base unit is gram. All right. Well, the way that we've come up with atomic masses, average atomic masses, they've been mass assigned, and if the value that we see in the element boxes has an AMU attached to it, that means it is referring to an individual atom. So we would say the average boron atom is 10.81 AMUs. Now, as we'll see, of course, we don't deal with individual atoms or even handfuls of atoms. That would be impossible. So practically, we do replace AMUs with grams when we're working in lab. But whenever we're looking at calculating average atomic mass, very commonly we'll be using AMUs. Again, only in Chapter 3, and the application is when we're talking in terms of atoms of the element, not moles of the element, which will be the next lesson. All right. There is not any expectation, of course, that you will know the different isotopes of every element. But if you were given this information, as well as the percent abundance of each element. So we've gone through that there are 3 forms of carbon. And if we see, we encounter the carbon-12 form 98.90% of the time, and about 1.10% of the time, it's carbon-13. And this is not even enough to do the calculation for, so we just ignore that. So if ever an isotope is found in trace amounts, we don't even take it into account when we're calculating the weighted average. Now you are told that carbon-12 is assigned 12.000000 AMUs. And then carbon-13, okay. So if we were given this information, how would we find the average atomic mass, a weighted average? Well, first, we know that mathematically, we can't do further math when we're given a value as a percent. So the very first thing we have to do is undo the percent or divide each of these by 100. Next, we multiply each atomic mass by the percent abundance divided by 100. So we're gonna multiply these. All right, so what we get when we do the multiplication for carbon-12 and carbon-13, we will get, and we obey significant figures, of course, 11.87 AMUs. And then for carbon-13, we get 0.143 AMUs. All right, then we add these. When we add, and we'll respect number of decimal places, we get 12.01 AMUs. And don't you know, that is the value of the average atomic mass of carbon. It is a weighted average. We simply didn't add these and divide by 2 because this represents the average carbon atom. There is not one single carbon atom that has the mass of 12.01 AMUs. Not one. But if you would have a handful of carbon, the overwhelming majority is this version. So the average, weighted average, will favor the version that we encounter most often. If you are given, again, this information, so if you are given the different isotopes, their percent natural abundance, and then their individual masses. Again, first thing we'll do is divide each of these by 100. Then we multiply that by the atomic mass, and then we add them. And what we should get should match the value on the periodic table. I have worked out the rest, so if you want to give another one a try, before I did the math, of course I divided these all by 100. So please take that into account, even though I just, wrote that for here. But you'll see then these are the resultant values, and then when I add those, I get these final weighted averages. So that is how we calculate the average atomic mass.